So thanks everyone for being here. It's really my pleasure to be introducing this tutorial on the exciting intersection of hardware algorithms and for efficient deep learning. And I'm also quite pleased to announce that Vivienne is going to be giving the tutorial. She's an associate professor at MIT in the EECS department, and she has many, many contributions to the field, to many fields actually, including signal processing, circuits, and systems for a variety of applications such as computer vision, deep learning, video coding, and so on and so forth. She did study in University of Toronto in 2004, where she got the bachelor's degree, and then later did master's and PhD at MIT, for which she got the outstanding doctoral thesis award in 2011. And she's gotten many, many faculty awards from companies such as Facebook, Qualcomm, or Google. Also, 2014 Young Faculty DARPA Award, and many, many other awards, the coolest of which I think is maybe the 2017 Primetime Engineering Emmy Award. So that's for contributions to video compression, for her contributions and the team. And so I think we're very fortunate today to be here attending this tutorial by Vivienne, and then without further ado, we can begin. Just to say that there's going to be a short break, about 5 minutes for maybe bathroom or questions, and that's it. Let's thank the speaker for being here. Super exciting.
All right, great. Thank you very much. Yeah, so it's great to be here, and excited to share with you guys today about the field of how to enable efficient processing for deep neural nets. Before I begin, we put together these slides. This is in collaboration with various folks, so Jianru Yang and Yushin Chen, who are my students and former students, and then Joel Emmer, who is a collaborator of mine. And then the slides are all available online as well, so if you want to follow them during the talk, feel free. So we know that over the past few years, the field of deep neural networks has been very exciting, but the compute demands for deep neural networks has also increased substantially. So very recently, OpenAI reported, for instance, that over the past 7 years, the amount of computation for training these nets has increased by over 300,000. And at the same time, most recently this year, it's been reported that these have significant implications also in terms of carbon footprint. So for instance, the cost of training a large transformer is orders of magnitude higher in terms of carbon footprint compared to things like a flight, human life, or how much the carbon footprint of a human in 1 year, or even the lifetime carbon footprint of a vehicle itself. So these are significant challenges, particularly in the cloud. Another area which is also important, if we care about kind of the deployment of AI, particularly for a wide range of applications, is being able to move the processing for deep neural nets from the cloud to the edge itself. And there's many compelling reasons why we would want to do this. So the first reason is if we want AI or this technology to be accessible to people around the world, we really want to reduce its reliance on the communication infrastructure, because there's no necessarily guarantee that you'll have a stringent communication infrastructure around the world itself. Another reason you might want to move the computing to where the data is being collected at the edge is for privacy reasons. So there's a lot of exciting applications for neural networks in spaces like healthcare or in the finance area where you're dealing with very sensitive data, and you might not necessarily want to send that data to the cloud itself. You want to keep instead you want to bring the compute from the cloud to the edge where the data is being collected. The final reason is when we're thinking about applications that involve interacting with the real world, for instance in robotics or autonomous navigation, latency is really critical, so the reaction time. So for example, if you're driving very quickly on the highway and there's an obstacle, you might not have enough time to send the data to the cloud, wait for it to be processed, and be sent back. So because of the latency constraints, again, you want to move the compute into the vehicle, into the robot, and the device itself. So these are all the various reasons why we want to move the compute from the cloud to the edge. And again, one of the main challenges for doing this is actually power consumption. So if we again take self-driving cars as an example, it's been reported that in order to process the gigabytes of data that's being collected in these autonomous vehicles, you can typically consume over 2,000 watts of power just for crunching the data that's being collected itself, and this results in a huge amount of heat dissipation and even requiring some water cooling. Okay, and then this challenge is going to be even more significant when we start shrinking down the size of the device, perhaps into something that might fit in the palm of your hands, for example, your phone. In these particular cases, these portable devices, they're often battery operated, but the size, weight, and cost of the battery is limiting the amount of energy that can be stored in the battery itself, or the battery capacity. So you have a limited amount of energy that you can consume in these particular devices. In addition, for these devices, you typically do have some form of a power ceiling, typically under a watt because of the heat dissipation for carrying the device. And existing processors that do this type of processing typically consume an order of magnitude above that limitation itself. So in the past, what we would do is we could just wait for better, faster transistors. However, these transistors these days are not getting more efficient. So if you look at Moore's law, which means the scaling of the transistor to reduce the size, meaning transistors are getting smaller and faster, and Dennard scaling, which means that transistors are getting more efficient, we can see that these trends are slowing down. Over the past couple of years, they've really kind of flattened out. Right, so as a result, these general purpose processors are not getting faster and more efficient. We really need to come up with new solutions to meet the compute demands for these emerging technologies of AI and neural nets. So one of the approaches that people have been taking to address this is to design specialized or domain-specific hardware to achieve these speed and energy efficiency improvements. Okay, so there's a lot of exciting activity in this space. So what are the goals of this tutorial itself? So in fact, because this is a huge pressing problem for the deployment of AI and the advancements of deep neural nets, there's many approaches to efficient processing of DNNs that are being currently explored. So for example, I'm sure you have all seen this plot in terms of kind of the rise of machine learning papers on arXiv, how it's exceeding Moore's law. You have over 100 new papers a day, and a lot of this is driven by neural nets, which is a key component of, key form of ML. So it's actually not possible for us to cover, all the particular techniques that are, coming out today. In addition, if you look at top hardware conferences, the rise in the number of specialized hardware and research for deep neural nets is also increasing rapidly. And then if we also consider from a commercial aspect, New York Times reported that there's a huge number of startups just really focusing on building specialized hardware, specialized processors for deep neural net itself. So again, we can't possibly cover all these techniques within a 2-hour tutorial. So the goal of this tutorial is actually going to do as follows. Actually, the focus is more how do you evaluate all these different approaches to efficient deep neural network processing. That's really the goal that we want to achieve today. In particular, when we say approaches, we're going to cover both the design of deep neural network hardware processors as well as the design of the neural network models or the algorithms themselves. And really, what I hope you guys all get out of this tutorial is to learn what are the key questions to ask when you're trying to read these papers, or you're reading spec sheets on these particular topics so you can actually understand what's going on in the space itself. In particular, what we're going to focus on are what are the key metrics for evaluating these processors. So when we say efficient deep neural network processing, what exactly do we mean? What are the metrics that should be measured and compared? What are the key challenges towards achieving these metrics, right? So what are the limitations? Why is it a difficult task? And what are the design considerations and trade-offs that we should be keeping in mind when we're evaluating the different types of approaches? Because often in all these spaces, there's often a trade-off between the various different metrics, and we should be aware of those. In this tutorial, we're going to primarily focus on inference. We'll touch a little bit on training, but primarily we're going to focus on inference. But a lot of the concepts also apply to training itself because we can view kind of inference as a subset of training. So a lot of these techniques also extend. To give you guys an idea in terms of the coverage of the tutorial itself, so we're going to start off very briefly with a quick overview of deep neural nets. This is more, I'm sure you're all familiar with this topic, this is more from a terminology point of view, just because this, neural nets have really taken off for a wide range of fields. Different terminology is used for the same thing, so I just want to kind of explain what is the terminology we'll be using in today's tutorial. Then we're going to talk about the key metrics and design objectives. Then we'll talk about the design considerations for various platforms from CPUs and GPUs to ASICs. We'll take a quick 5-minute break for Q&A between that, and then we'll, for the second half, talk about the algorithm hardware co-design, so how do you build efficient deep neural network models, talk a little bit more about other platforms that are emerging, and then also tools you can use to systematically evaluate all these DNN processors. Okay. So let's get started. So the very first thing is, okay, what are deep neural nets? I probably don't have to explain it too much to you guys, but it's basically we have a stack of these different layers that are extracting from low-level features from the right-hand side, from the left-hand side of this graph all the way to the right-hand side. So each of these layers, as you go deeper and deeper, you'll generate higher-level features. The key idea is that the weights to extract these features are all learned. Just a quick thing in terms of, again, for the tutorial, we have this color coding. We're going to have blue is typically going to represent the input feature map or input to a given layer. Green is going to be representing the weights of the filters or of the connections, and then red is typically representing the output feature map and partial sum. So just keep that in mind. We're going to stay with that color coding throughout the entire tutorial. But in general, again, we're stacking all these layers together, and this is why we refer to it as deep, is the depth refers to the number of layers itself. At each of these layers, what are we actually doing? It's actually a very simple operation. It's a weighted sum, right? So for each output activation, it's going to be a weighted sum of the inputs multiplied by some weight, and then we pass it through some nonlinear function. Could be a sigmoid, ReLU, and so on. There's many more. The main thing I want you to take away from this side is that the key operation is usually multiplies and accumulates. And this really accounts for over 90% of the overall computation in deep neural networks themselves, right? So if we're going to look at ways to accelerate or make neural networks more efficient, we really need to focus on reducing the cost of these multiplies and accumulates. And it seems pretty simple, but there's a lot of challenges in terms of addressing these MACs themselves. Another just quick thing in terms of the types of layers we might have in a DNN, right? We have kind of two categories in terms of the ways to describe it. You can talk about its feed forward, feed back, fully connected, or sparsely connected. So for example, a fully connected layer is a feed forward network where every output is connected to every input, and you would find this in a multi-layer perceptron. In convolutional layers, you still are a feed-forward type of network, so the inputs are connected, driving the outputs. They're going to be sparsely connected, so not every output is not going to be connected to every input, and often there's shared weights, meaning the same set of weights are going to be used across multiple outputs. And these are typically used for images. Recurrent neural nets, so in this case, recurrent layers, you're going to have feedback. The output is going to be fed back into the input. These are typically found in recurrent neural nets, and we typically use these for sequential data like speech and language. And then most recently, what's been really popular is attention layers or attention mechanisms. Attention typically looks at doing matrix multiply and combination with some feed-forward and fully connected layers, and we now see them a lot in things like transformers. Okay, so these are just at the very high level in terms of the types of DNNs that exist out there. Very briefly, just to dive a little bit deeper into convolutional neural nets, which we'll use as a driving example in this tutorial, but again, the techniques apply broader than CNNs. In a CNN itself, it does convolution, so you might have a filter which is composed of weights, and the dimension of the filter, for the terminology we're going to use in today's tutorial, is going to be R by S, so the height and the width of the filter, and it's going to be convolved with an input feature map, which is composed of activations. The size of the input feature map is going to be H and W, so height and width. We do an element-wise multiplication of the weights and the activations. And we sum them all together. That's called partial sum, when we sum the products of these together, and it generates one output activation in the output feature map. And the output feature map, the dimensions are E and F as well. All right, and so convolution, you would just basically slide the filter across this input feature map or input image and repeat this operation to generate multiple output activations. And so this is actually very standard for image processing. This has been done for decades. I think the main challenge when it comes to CNNs or neural nets is just basically the dimensionality. So in addition to doing these 2D convolution on the 2D images, you have a third dimension, which we refer to as the channels, right? So you have many input channels. We're going to use the letter C to denote the input channels. So you're actually going to do these 2D convolutions across each of the channels and then sum up their values across channels to generate one output value. Or output activation, and of course the size of the channels can be quite large, from 3 to 192 and even larger. This is just using Eyexam as an example. Another dimension where we increase is the number of filters we apply to the same input feature map. So in this tutorial we're going to use the word letter M to denote the number of features. So the number of filters. So if you apply M filters to the input feature map, you're going to generate M output channels. So every filter that you apply to the input feature map generates one channel. So if you have M filters, you have M output channels. And again, you can have hundreds of these filters for a given neural net. And then finally, there's the batch size. So if you're going to process more than one image at a given time, you're going to have a batch, we refer to it as batch size. You have a batch size of N. So if you have N input feature maps, you'll have N output feature maps. So basically these are all kind of the definitions of the various parameters, or basically defining each of the dimensions of the DNN layer itself. So we refer to this as the shape of the layer itself, right? So you have H, W, C, R, S, M, E, F, and N, and these can vary across the different layers. And so the variation of these dimensions is what also poses a challenge for doing efficient processing, because the more variation you have, the more challenging it is to build an efficient processor itself. And then finally, as an example, we know even modern CNNs, for example, MobileNet v3, we can see that the filter sizes, number of filters, and number of channels are going to vary across the layer itself. And then the other important trend that we've noticed over time is that over the past few years, as we increase the accuracy or reduce the error of these neural nets, we can see that the models are getting deeper. So for example, the number of convolutional layers in these CNNs are increasing, and also the size of the model in terms of the number of weights and the number of operations, number of max you have to do is also increasing as well. Right, so these are trends that it becomes increasingly more challenging to process these neural nets over time. Okay, so that hopefully is a very, very quick overview on the terminology that we'll be using in this tutorial. Now I'm going to dive into, well, what do we mean about when we say efficient processing of deep neural nets? In particular, what are the key things that we should be evaluating when we want to determine whether a given DNN is efficient or not? The key thing I want to emphasize here is, in terms of these metrics, it's much more than operations per watt. Typically, when people refer to a system that's very efficient for processing DNNs, they talk about, flops per watt or tops per watt. And what I really want to highlight is that there's many more metrics than just that to define the efficiency of the neural net system itself. So the first thing is obviously accuracy. So the quality of result really matters. That's why we're all very excited about DNNs. When we're looking at accuracy, of course, it's also important to consider the accuracy or consider the difficulty of the task or data set that we're using to measure the accuracy. So having high accuracy on ImageNet is different from having high accuracy on MNIST, for instance. Throughput is also very important. Throughput basically refers to how much we can process per second. So this is going to be very useful for applications like analytics on high volume data, which you would typically, for example, do in the data center. It's also really important for cases like real-time performance. So for example, if you're capturing video at 30 frames per second, you want to ensure that your processing will be able to keep up with that. Latency is also really important. Now, latency and throughput are different. So latency is important for interactive applications, for example, autonomous navigation, and it really dictates the time in which, when you capture the data and when you can actually provide a result. That dictates latency. Latency and throughput can be different in the sense that often to achieve high throughput, we might group a lot of information together and process it together to achieve high throughput, but you couldn't really do that for latency. So a very typical example we give in class is like if you're talking about doing laundry, right? You typically collect all your dirty laundry across a week and then process it, and so the average time per sock is going to be reduced, but if you really need to wash that sock, you have to do one sock at a time. You don't want to wait an entire week to batch all of your data. So that's how latency and throughput is different. These are all very critical. Energy and power consumption are also important. So energy is typically what we think of when we're looking at embedded devices, which are battery operated. And as we mentioned, the battery capacity is limited by the size, weight, and cost of the device. You have limited energy. For power consumption, it's often a limitation in the data center, primarily due to the power ceiling that you would have for these particular devices. This is due to the heat dissipation itself. So when the power consumption is very high, it's going to generate a lot of heat and you need to cool it. And so that's really going to limit how much power your system can consume. Another really important thing is cost, right? So the cost of the system really dictates whether it's going to be accessible, how widely it's going to be deployed. Typically in the context of building custom hardware, for example, cost might refer to the size of the chip or the process technology that's being used, but it could also refer to the infrastructure around the system, for example, how much bandwidth is required. Also, flexibility is really important. So we're now seeing deep neural nets used for a wide range of applications, and we also see a wide range of deep neural network models. I just want to clarify, deep neural network models often refers to like network architectures, but we're trying to avoid the word architecture just because we are also talking about hardware architecture, so we're going to call them deep neural network models. But there's a range of models that you actually want to be able to support, so flexibility of the hardware is key. Also, given that this is a very fast-moving field, we know that it takes some time to build the hardware, but you want to kind of future-proof and be able to support future DNN models as well. So flexibility is very critical. And then scalability is a really important metric. So the idea here is that if I give you more resources in terms of more cores or more max and more memory, the performance should also scale up equivalently. That would be the ideal situation. So how well does your design, in particular your solution, scale up with more resources? So we'll jump in a little bit deeper for each of these particular metrics. So the first thing is throughput and latency. So we want to increase throughput and reduce latency. So what are the different strategies that people at the very high level, what are different goals that feed into these type of metrics? First is we want to reduce the time per multiply and accumulate per MAC. So this could be what we call reducing the critical path of the circuit, or in other words, running at a higher clock frequency, making higher clock frequencies possible. In the case of more programmable solutions, we want to reduce the instruction overhead, so the number of instructions you have to issue to perform that multiply and accumulate. The instruction issues can be very expensive. You can reduce that. That would be better. Can we avoid unnecessary multiplies and accumulates? So we'll, kind of as a hint forward, there are cases where you don't need to necessarily multiply by a 0. You can skip those multiplications, and if you can skip them, you can save cycles and run at a higher throughput. You might also want to increase the number of processing elements we have, and by processing elements we mean multiply and accumulate engines. So if you can do more multiplies and accumulates in parallel, you're also going to go faster. Now this can be achieved by either increasing the area density, meaning basically reducing the area cost per processing element, or it's just going to be basically increasing the cost of the system in order to achieve this form of parallelism. What's also really important is actually not just how many multiplies and accumulates or processing elements you have, but can you increase the utilization of these processing elements themselves. So in the ideal situation, if all of these processing elements that you've put down are running, you have 100% utilization. You can keep them all busy, they're all doing work, that is great. But it's actually quite difficult to achieve, and there's a couple of things that you want to do in order to keep all of these processing elements busy. So for example, you want to ensure that you can distribute whatever workload you have to all of the processing elements so they can reach all the different processing elements, so they're all assigned work to do. You want to make sure that the workload is balanced across all of these processing elements, because typically, the one that gets the most work might be limiting the overall throughput of the system, so balancing that workload is also an important challenge. And then also having sufficient memory bandwidth to deliver the workload to the PEs themselves, right? So it's not just a matter of making sure that it's balanced and that it's reaching everybody, but you want to make sure that these particular processing elements are not data starved, that you actually have enough memory bandwidth to deliver the data to keep all these processing elements busy, in other words, reducing their idle cycles. And so these are all going to contribute to ensuring that all the processing elements that you've laid down, that you've paid area cost for, they're actually all going to be working towards the goal. So these, all these constraints actually also affect latency, but low latency has an additional constraint that you need to really reduce the batch size itself. So for many applications, for example, in autonomous driving, you might not be able to wait for, multiple images to be processed at a given time. Once you get a certain image, you might only do a batch size of one to process that image. To delve slightly a little bit deeper, just to show that in terms of actually evaluating performance or throughput, there's actually many factors that, again, affect this. There's a framework called Eyexam, which gives us basically a systematic way of understanding the performance limits of DNN hardware as a function of the various characteristics of the DNN model and the hardware design itself. And so this can be found on arXiv. And so basically there's two axes to this plot. There's a vertical axis, which is the max per cycle. So the higher, the better here. That means you're going to be able to process at higher throughput. And then there's also max per data on the x-axis, which is basically telling you for every given piece of data how many operations you can actually do itself. So the first thing that kind of tightens or limits the maximum number of MAC operations you can do per cycle is going to be the DNN model itself in terms of what is the maximum parallelism that you have in the DNN. So how many, if you have infinite amount of hardware, how many of those multiply and accumulates could you do in parallel within the DNN model? The second step that kind of tightens this upper bound is going to be the data flow itself. We'll talk a little bit more about that, but that basically dictates in what dimension are you doing the parallelism. Are you parallelizing across the weights, the input activations, the output activations, and so on. And then what really starts, where the hardware kind of kicks in is start looking at what is the maximum, or basically what are the number of processing elements that you're going to put down in the system itself. And so this is going to be the theoretical peak performance. You often hear when people release a new product, they talk about, I have this many cores, this is my peak performance. So this is the upper bound that can be achieved. And there's going to be a slope here, which is basically indicating the limitation due to memory bandwidth. So this is actually an extension of the roofline model, which is typically used to analyze computer architectures, right? So you have the peak performance, which is the number of PEs, and then the slope shown here is due to the bandwidth to the PEs, the memory bandwidth. Can I actually deliver data to these processing elements to make them work? Right? And then where you might sit on the horizontal axis in terms of max per data really depends on your workload itself. So you can be compute bound, which is the case where you have a lot of multiply. For one piece of data, you can do a lot of multiplies and accumulates, and that way the performance is really limited by how many computation engines or processing elements you actually have. On the other hand, if you have workloads that have you can only do very few multiplies and accumulates for a given piece of data. So for example, fully connected layers, then you might be bandwidth bound itself. So the speed at which you're going is limited by how well you can actually deliver the data itself. Compared to compute bound, usually convolutional layers are more in the compute bound regime itself. Okay, so so we already have this roofline model that limits the throughput based on the number of PEs, but then there's other design decisions that also further reduce the maximum throughput you can achieve. So for example, what is the array size itself? So you might have an array of these processing elements. So the dimensions of these arrays, the height and width of the array, as well as the storage capacity of this array, might limit how many of the processing elements in the array itself can actually be enabled at a given time, right? So just because you have 1,000 processing elements doesn't mean all 1,000 are going to be allocated work. So that further reduces the maximum throughput that you can achieve. And so in fact, you actually get another modified roofline model that's actually much smaller than the peak promised roofline model that you would get for number of PEs. So we show here in red. And again, here, this is all the limitations in terms of the bandwidth to feed the active PEs. So this is, red line here is just basically showing the roofline model of the active PEs within your processing element array. And then furthermore, this can be further tightened up by basically the bandwidth to deliver the data to those active processing elements. So this could be first the average bandwidth to deliver to those processing elements, and then also instantaneous bandwidth. So if the bandwidth really fluctuates a lot, right, so sometimes you need a huge amount of data and sometimes you don't. If you take that into account, the performance can be much lower. Again, I think it's worthwhile to walk through this later on when you have more time, but the key message I just want to get across from this slide is even though you might have a lot of processing elements and you can claim I have a lot of PEs, in reality your overall throughput is going to be further reduced, might be much lower than that because of various design decisions that are made in the hardware. And this is really the challenge in terms of hardware design. How do you kind of raise this operating point further up? Okay, so that's throughput. The other thing that's really important, as we mentioned, is energy efficiency and power consumption. So the first thing you should note is that actually, as it turns out, the energy that's being consumed is not dominated by the number of max that you're doing it at all. So shown here on the right-hand side, you can see in blue the energy that's being consumed for multiplications and additions for different levels of precision. What's actually dominating power consumption is actually data movement. So the cost of moving the data from the memory to the multiply and accumulate engine itself. So for example, reading the data from this small on-chip memory, let's say 8 kilobyte SRAM, is going to consume more energy than a 32-bit floating multiplier. And then this is going to be even worse if you're reading the data from off-chip. So for example, if you read the data from DRAM, it's going to be even more expensive. We're talking about orders of magnitude increase in energy costs for moving that data around itself. So keep in mind here the x-axis is on an exponential scale. So one of the key things that are important in terms of designing efficient hardware for processing anything, but in particular for deep neural nets, is to try and minimize this data movement. And what we can do is we can exploit what we call data reuse, meaning that if I read the data once, can I use it multiple times for multiple operations? And we'll get into more detail about this. So that's the first takeaway I would hope you get, is that it's really dominated by data movement. That's where the energy is going. You can also look at reducing the cost of the Mac itself. For example, you can reduce the switching activity or the capacitance of the Mac with better circuits, and you can also reduce the instruction overhead. Again, if you have a programmable solution, if you're issuing a lot of instructions, can you reduce the number of instructions you're issuing, because those instructions also are energy costly. Of course, similar to throughput, another important thing is just avoid any unnecessary max. If you don't have to perform that mac, right? Again, if you're multiplying by 0, for example, you should just not perform it, and then you'll save a lot of energy there. And then finally, just to link power consumption to the throughput itself. Power consumption, as I mentioned, does also limit the throughput, because power consumption is limited by heat dissipation. And so this is going to limit the number of parallel macs that you can actually perform, which means you're going to limit throughput as well. Right? So if you can address power consumption or energy consumption, you can help increase the throughput of your overall system. Another important vector that we should think about is flexibility. Again, because this is a very fast-moving field with a lot of different variations in the DNNs, it's really important to have the flexibility in the hardware to be able to support today and tomorrow's DNN models. But the key challenge from a hardware perspective is that often there's going to be some overhead to support this flexibility. Nothing comes for free, so the key challenge is how do we reduce the overhead to support this flexibility? And what kind of flexibility do we need, or what do we actually mean here? We mean, first of all, we want to be able to maintain efficiency across a wide range of DNN models, and this could include different layer shapes, which can impact the amount of storage and compute requirements, and also the available data reuse that can be exploited to reduce the data movement costs. The different precisions that you might have across layer and data types. So for example, the weights, activations, and partial sums might all have different precisions. Can we have flexibility to exploit that? Different degrees of sparsity, right? So I could have very sparse data or very narrow or very dense data, and sparsity refers to basically the number of zeros you might have in your weights and activations. And then also in general, like the type of DNN layers, can I support convolutional layers, fully connected layers, recurrent layers, and so on, and also computations beyond MAC itself, like various different activation and pooling functions. So flexibility is very important, and then finally scalability, as I mentioned, is also really key. The key idea here is that if I have one given design and I say I want to put more resources into it, for example, increase the number of PEs, increase the amount of memory, does the performance, for example, the throughput naturally scale up, or the efficiency, energy efficiency naturally scale up if I'm going to allow it to have more memory? And that's also really important. This allows you to avoid having to redesign the hardware or system every single time you get more resources. For all of these different metrics, it's important to kind of drill down a little bit more to ask more, because sometimes people report these metrics but not, give the inside or lower level information. So for example, I probably don't have to say it too much here, but and when you're looking at accuracy, it's important to, again, assess the accuracy. It depends on what type of data set you have and what task you have. So it's much easier to get higher accuracy on, let's say, MNIST than ImageNet, or even a more advanced type of data set. So that's really key. And the reason this is important is because for difficult data sets, you typically need a more complex DNN model. So obviously, a more complex model is going to result in higher energy consumption. Right, so for an apples-to-apples comparison, it's important that the models are the same or of the same complexity. For throughput, again, looking at not just the number of processing elements, but also considering the utilization of those processing elements is really important, right? So in particular, when you're looking at throughput, you might actually ask for the runtime of a specific DNN model. You might not be satisfied for someone telling you I have 1,000 cores or 10,000 cores or whatever. The more important thing is asking how many of those cores are actually being used, or even more specifically, when I run these DNN models, how much time is it actually taking? Latency is really important. So if people report the throughput, you might also ask, what is the latency, what is the batch size, because that might be really important for your particular application. Energy and power consumption. So again, you want people to report the power consumption of running specific DNN models. Another thing just to be aware of too is, as we kind of hinted or mentioned, accessing data from off-chip, let's say from the DRAM, can be very expensive. And so it's not sufficient for people just to report the power consumption of their, let's say, processor or chip alone, but it's also important for them to kind of report the off-chip memory access, how much data it requires to access off-chip, because that will contribute to the overall system power. Hardware cost, right? So these are things that are going to feed into the cost of the system. So how much on-chip storage is required? How many processing elements are there? What is the area of the chip itself? What is the process technology? Obviously, when you're comparing various different systems, you don't want to compare a very cheap, low-cost system with a very expensive system. That's not going to be an apples-to-apples comparison. So the cost should always be factored in. And then, of course, flexibility is very key. You often want, you want a processor that doesn't just, design for one particular, neural net. You want it to support a wide range of neural nets. So, you might often ask, can you report the performance across a wide range of DNN models? And in fact, often it would be ideal if specs would define the range of models that it can efficiently support. So these are all the various different metrics. I just also want to walk through an example of how you could actually utilize these metrics to make various evaluation and design decisions, right? These should all be reported. So for example, I'll just first give you an example of what could happen if people don't report all of these metrics. So for example, if accuracy is not reported, or if it's not reported with a specific data set or a task, you could imagine one could run a very simple DNN model and then claim their system is very low power, high throughput, low cost. However, when you try and use that processor for a more meaningful task, it's not going to work, right? So that's why accuracy on what data set is really important to be reported. Another example is if people report the the power consumption of the processor, but they don't actually include off-chip memory access. You could imagine that you could build a processor with only multiplies and accumulates, and then you could claim low cost, high throughput, high accuracy, low power consumption. But then when you actually evaluate the chip or the processor in the context of an actual system, the off-chip memory access could be very substantial. It could be very limiting to the overall solution there as well. Right? So this is just two examples in terms of why it's really important to get all those metrics reported when or thinking about all those metrics when you're evaluating different systems or different papers that you're reading. It's also really important just because this area has also taken off. So there are publications and specs that have been measured and then things that have been simulated. There's a big difference in terms of measuring and simulating things. Whenever you're actually fabricating chips, you have to build in a lot of margin. So that should also be something that you take into consideration when you're evaluating various solutions out there, and on what data was it actually tested. So just as a very quick example of how you might walk through these different metrics in terms of making a decision, for example, whether or not a various DNN processor or technique is good for your particular application or a viable solution for your application, you might start out by saying, so of course, what is the accuracy for a given task that you care about. So the accuracy determines if it can perform the given task that you care about. If it doesn't reach the accuracy that you need, I mean, maybe it's already like a moot point that's you don't care about anymore. Assuming it can give you the accuracy that you need, the next question you might ask is what is the latency and the throughput? And this will basically tell you if it can run fast enough and in real time, which might be important if you're doing interactive applications. Then you might ask about the energy consumption and power consumption, and this will primarily dictate the form factor of the device and where the processing can operate. Can it happen in the cloud, or can it happen in a handheld device or at the edge itself? If it satisfies 1 to 3, then you can say, okay, what is the cost of this particular solution? And this is often, when you're talking about specialized hardware, this is going to be dictated by the area of the chip. And it basically would dictate how much one would pay for this solution. And then finally, if you want to be future-proof, you want to support many applications or many different models, you might also ask about the flexibility and its efficiency across a wide range of tasks itself. Right, so again, I just want to further emphasize that it's important when you're evaluating all these different efficient processing solutions out there, whether it be hardware or even from the algorithm co-design side, to think through all these various different metrics, because often in the design there's some trade-off between these different dimensions. Okay? So with that, I'm going to start looking at various different platforms and describing, kind of classifying the different areas that people focus on in terms of achieving these metrics. Again, the idea is to more kind of organize the different topics or different approaches people use, but not exhaustively go through all the different approaches. So the first thing we're going to start with are CPUs and GPUs. These are probably the most commonly used platforms for deep neural network processing. And in fact, over the past few years, because of the popularity of deep neural networks, there's been a lot of, CPUs and GPUs that are specifically targeted at DNNs, right, ranging from Intel, NVIDIA, and AMD. And often what ends up happening for these particular systems is they often use the matrix multiplication libraries in the CPUs and GPUs to process the DNNs themselves. Right? So first I'm going to talk about how we map the neural network to matrix multiplication. In the case of fully connected layers, it's a pretty easy mapping from the fully connected layer to the matrix multiplication itself. So in a fully connected layer, the way that you can view it is that the dimensions of the filter exactly match the dimensions of the input feature map, right? So here you can see that the dimensions of the filter HWC is the same as the dimensions of the input feature map. So for the element-wise multiplication, there's no sliding like in the convolution. You just multiply each of those values together, and they'll generate one output activation through that dot product. You can imagine what you would do is to take this, you could flatten it out into matrix itself. So the filter matrix here would be the height of it would be the number of filters, and then the width of it is going to be the dimensions of each filter itself. So like the number of weights in a given filter, so CHW. The input feature map matrix would be basically, again, the height of it would be the number of activations per feature map, so CHW again, and then the width of it would be the number of feature maps or number of images you're processing, so the batch size. Right, and so you could do, and then basically your output feature map would be like the height is going to be the number of output channels or output filters, and then the width is going to be the batch size itself. And then for, as you do matrix multiplication, one row times one column is going to generate one output. So in fact, so you can easily map a fully connected layer to matrix multiplication, and matrix multiplication is obviously also heavily used in recurrent and attention layers as well. So this is often why you hear a significant portion of the workload for DNNs has to do with matrix multiplication. And as we mentioned, GPUs and CPUs naturally have matrix multiplication libraries that are accelerating this operation. The convolutional layer itself can also be converted to matrix multiplication through using a Toeplitz expansion. So if you have a convolution here, right, you're having this 2x2 filter that's going to convolve across the input feature map. You can basically change this 2x2 filter into a 1D vector, so 1x4 vector. And you're going to basically use a Toeplitz expansion from the input feature map, which is 3x3, and expand it to 4x4, and then your output feature map, rather than 2x2, it's going to be 1x1, to kind of follow what's going on. Let's say you do an element-wise multiplication of this filter, 2x2 filter, with these 2x2 feature map. input feature maps. The equivalent in the matrix multiplication will be this, or vector matrix multiplication will be the 1/4 of the filter with one column of the input feature map that's been expanded. Now the key thing, so this is fine, this is a great way to map the convolutional layers to matrix multiplication, and as we mentioned, CPUs and GPUs have very optimized libraries to perform matrix multiplication. Well, the one thing I do want to highlight, though, is that by doing this expansion, what's actually happening is you have a lot of now repeated data in the input feature map. So before, it was just a 3x3 feature map, and now we've expanded in this toy example to 4x4. There's a lot of repeated data, which means that this is going to increase your storage cost and data movement. Right, so even though you can easily map it, there is a cost for doing this mapping. It's not coming for free, but nonetheless, because these platforms can efficiently support matrix multiplication, it's worthwhile doing. That's what's really done. In particular, for these CPUs and GPUs, they have these various different libraries to accelerate matrix multiplication, and the matrix multiplication, the libraries will note the various different shapes of the matrix multiply and select the right implementation that's optimized for that given shape, so meaning the dimension of the matrix multiply. And often the optimization also involves what we call tiling to the memory hierarchy itself. So you might have some on-chip storage in these GPUs and CPUs, and you want to be able to fit your processing in this on-chip storage. Just very briefly in terms of what that actually means. So, so let's say you have, this is the same matrix multiplication that we saw before, and typically you would take this full row of your filter multiplied by a full column of your input feature map and generate one output, and then you'd go across all the rows and across all the input feature maps and generate the output. The challenge here is that the size of this matrix might not actually fit on your on-chip memory, and if you remember again, on-chip, going off-chip is much more expensive than staying on-chip to fetch your data. You always want to keep the data on-chip if you can. Right? And so if this is too large, what you can actually do is tile it. So you take your matrix, break it up into smaller tiles, as shown here, and now you're just going to do the matrix multiplication of these particular tiles to generate your output. For example, this would be in step 1. So you can imagine all of this could fit on chip, and so now the access for these values are going to be cheaper because you're accessing them from an on-chip cheap memory as opposed to an off-chip DRAM, which is much more expensive. And then in step 2, you would move towards the next tile. So clearly here, this is not completing the output, so you would have to look at the next 2 set of tiles to finish generating the output itself. Okay, and then you would imagine iterating through the different tiles to perform this operation. So again, what the compiler is doing is it's trying to select what is the right tile size so that we can fit that all onto the on-chip memory, which is much cheaper. Okay, so that's tiling the matrix multiplication. Another thing that we want to do in terms of accelerating the processing is reducing the number of operations. And so the compilers actually do this in order to just explain how you can reduce the number of operations without affecting the final result. We'll use Gauss's matrix multiplication algorithm as an analogy. So for those of you who remember doing complex multiplication, you have the real and imaginary parts. You're multiplying 2 complex numbers, and your result is going to also have a real and imaginary part. If you did this in a straightforward way, this would be 4 multiplications plus 3 additions, right? So the multiplications are AC, BD, BC, and AD, and then the 3 additions, we call subtractions also additions, would be the subtraction here and then these 2 additions. In Gauss's algorithm, what you can actually do is rather than directly computing it, you're going to compute these intermediate values. So K1 is C times A plus B, K2 is A times D minus C, K3 is going to be B times C plus D, and then you're going to combine these intermediate values to form the real and imaginary parts. And so why would you want to do this? Because if you first compute these intermediate values, now you only need to have 3 multiplications to compute 1 for K1, K2, and K3, and then you have 5 additions. But typically, your throughput is dominated or dictated by the number of multiplications that you actually do. So here, you've already gotten a 25% reduction in terms of the multiplications. So the key idea here is that you want to reduce the number of multiplications, and so as a result, you can increase the throughput of the overall system. Okay, so this is a toy example, but how it's actually applied for neural nets, there's a couple of approaches that people have taken, right? So you can do a Fourier transfer, a fast Fourier transform, and so this turns a direct convolution, which might have been to the power of, based on the number of outputs squared, a number of weight squared to basically the number of output squared log 2 number of out squared. The con of this, of course, is actually increases your storage requirements. You have complex numbers you need to store. Sometimes you need to pad the filter to match your input size. There's also stressing, which has been used for a long time for matrix multiplication. So basically from ON cubed to ON 2.8, right? So you get slight gain there, but there's some numerical stabilities here. Winograd actually has become very popular for DNN acceleration. So for example, using Winograd, you can speed up 3x3 filter by 2.25x. Right, but the main challenge here is that it's a really specialized processing. It depends on filter size, so you have to change the details of the transform depending on what is the size of the filter. And so basically what happens is the compiler will, based on the size of the filter and based on the storage requirements, kind of select which transform to apply for the DNN itself. All right, so what other things can you do in terms of a CPU and GPU to kind of speed up the processing for DNNs? Another thing is basically perform more multiply and accumulates per instruction, basically reduce the instruction overhead, right? So for example, in CPU, this often involves doing SIMD, so simultaneous single input multiple data. Basically, single instruction, multiple data, so one instruction, multiple operations, or in other words, vector instructions. So, for example, Intel has a specialized vector neural network instruction, basically can do multiply, it fuses the multiply and add instructions so that you only have to issue fewer instructions, do more operations. In a GPU, in a similar type of way, you have SIMT, so single instruction, multiple threads, or you can think of the tensor instructions. You might be familiar with the tensor core in NVIDIA's GPU. So again, they have a new instruction, which is the matrix multiply accumulate code. And so basically by issuing one of those instructions, you can then perform 64 max with the tensor core itself. Another thing that CPUs and GPUs have been doing is that it can perform more max per cycle without increasing memory bandwidth by supporting reduced precision. And we'll talk a little bit more about reduced precision after the break, but the idea here is that if I can, let's say, load 512 bits at a given time into the hardware, I can either support 16 32-bit max, which is the typical default, but if I can support lower precision, for example, 8-bit max, now I can support 64 max for the same input bandwidth. So if I'm only accessing 512 bytes per cycle, now I can support many more max than I could before if I can support reduced precision. So this is another kind of feature that you commonly see in GPUs and CPUs to increase their throughput for DNNs. Again, so what are some design considerations when we're looking at CPUs and GPUs, or kind of design focuses that they have? The first is, again, on the software or compiler side, what are the different transforms it can support so it can reduce the number of max or avoid very unnecessary MAC operations. There's also the various forms of tiling and scheduling the various different loop orders to increase the utilization of the processing elements themselves. So if I can, keep the data on chip, then my processing elements can also keep busy. From a hardware perspective, what are the different things in general they are doing? So they're trying to reduce the time per max. So you might see increased speed per PE, so increased clock frequency. Also trying to reduce the number of instructions that you have to issue per MAC. So you have these large aggregate, like vector or tensor-based instructions that we just talked about. One thing to note that this often requires additional hardware, right? So from the GPU or CPU manufacturer's point of view, they have to allocate more transistors to go do these types of special aggregated instructions. They often try to increase the number of parallel MACs themselves. So for example, they just have more PEs per chip, so they have more cores, for instance, but this is going to have an area cost for them. And then they, of course, as we discussed, you can support reduced precision and naturally get more MACs on chip. Finally, to increase PDE utilization, what do they typically do? Well, they could increase on-chip storage, right? So if you store more data on chip, you can keep your processing elements more busy, right? But this is going to come at an area cost. If you want to deal with off-chip data, they can also increase external memory bandwidth, right? So you hear things like NVLink, for example. These are things really focusing on increasing external memory bandwidth. This sometimes has an implication in terms of system cost. But these are the various kind of design considerations and strategies that CPUs and GPUs are taking in order to enable more efficient processing of DNNs. Okay, So that's existing processors, but there's also a huge space of designing specialized hardware just for DNN processing. And so we can refer to this as specialized hardware or domain-specific hardware. Okay, so first I'm going to talk about kind of the key principles of what you should be thinking about when you're designing these hardwares, and then also how these different hardwares differ. So the first thing is that there's, even though DNNs are very high dimensional, there's actually properties that we can really leverage to achieve high parallelism. In particular, or high throughput. In particular, a lot of these multiplies and accumulates can happen in parallel. So high throughput, like high speed, is actually very possible. The main challenge, which should be no surprise to you guys right now, is memory access, right, is the bottleneck. So again, how do you deliver the data to the multiply and accumulate engine is really what's limiting both the throughput and the energy cost. So I'll give you an idea why this is the case. So if you have a multiply and accumulate, a MAC, in order to perform that MAC, you need 3 memory reads. So the filter weight, the input feature map, and the partial sum. And then you have 1 memory write, another memory access to update the partial sum. So that's a 4-to-1 ratio in terms of memory access to the compute operation itself. Okay? And then as we mentioned, this would be absolute worst case if each of these memory accesses were from an off-chip memory, for example, DRAM, each access is going to be an order, or at least maybe 2 orders of magnitude more expensive than the operation of the MAC itself. Okay? So again, just taking a toy example, for example, AlexNet has 700 million MACs, it would require 3 billion DRAM accesses. And this would be consistent with, like, if you look at modern DNNs, that would be also the challenge you experience. However, there are properties of the DNN that you actually can exploit, in particular what we call input data reuse, meaning that a given set of inputs can be reused multiple times for many more operations. Right? So if I can read it once and put it in a low-cost memory and use it for many operations, that's going to be very helpful in terms of dealing with this memory access bottleneck. What are the different types of reuse that you can actually have? So in CNNs, you often have what we call convolutional reuse. So when we're sliding that filter across the input feature map, the same weights and activations are going to be used, but just in different combinations. So we refer to this as convolutional reuse. In both convolutional layers and fully connected, we have what we call feature map reuse, which is that multiple filters are going to be applied to the same input feature map. That means that each activation in the feature map is going to be reused multiple times across the different filters. Okay? So that's also great. And then the last thing that we have is if we decide to process more than one piece of input at a time, if we have a batch size greater than 1, then we can also have what we call filter reuse, which means that each weight in the filter can be reused multiple times across the different input images, okay, or input feature maps. So these are all great properties that we really want to exploit from a hardware point of view and from an algorithm point of view. The other thing I just want to mention is that there's as we mentioned, there's a lot of parallel processing that's enabled or feasible for DNNs, and there's 2 different paradigms that people take in order to enable this parallel processing. On the left-hand side here, we have a temporal architecture. This is typically what you would find in a GPU or CPU. So for SIMD and SIMT, basically you have a bunch of ALUs. So an ALU is just like a multiply and accumulate unit, so an arithmetic logic unit. They would share the same control, share the same register file, which is the kind of a local memory, before going up to the memory hierarchy, which would be like going to DRAM, for example. On the other side, you have what we call a spatial architecture. And basically what we are doing here is that for every ALU, or every multiply and accumulate, you give it its own local control and its own local storage. And so this is actually very popular for specialized hardware for neural nets, these spatial architectures. So each of these ALUs form what we call a processing element. So again, you have a multiply and accumulate within a processing element. You have a very small local storage. So for example, between 0.5 to 1 kilobyte of memory very locally right beside the processing element, and it has its own control. And then you also allow for all these processing elements to talk to each other. Right? So unlike the prior case where the only way the different ALUs can talk to each other is to go through the memory hierarchy, here they can communicate and share data amongst its neighbors. Right? So this is also very helpful because it's very expensive to go up to the memory hierarchy. If you can share data amongst your neighbors, or if you can read it from your small local memory, it's going to be much cheaper. And so really one of the design challenges that exist for specialized hardware is how do you take this very large neural network and then map it onto this type of specialized hardware where you have distributed memory and they're all communicating with each other. Basically you want to map this neural network onto this particular platform to increase the reuse of the weights and activations that we saw there, the input activations. We saw the input data reuse. And also you want to do a lot of the accumulations of the partial sums locally in the low-cost memories of these devices. Okay? And so the whole space to explore the various different ways we can map these DNNs onto these spatial architectures, we refer to it as the data flow, how the data moves through the system itself. Okay? And so there's a wide range of different data flows, and if you want to dig deep into it, I can refer you to this paper, but just very briefly to give you an idea of what these data flows are. The first thing is, again, re-emphasizing first that the data movement is expensive. So again, ideally, you want to have specialized hardware with small memories really nearby the multiply and accumulate engine. The reason for this is that having small memories is cheaper, right? So for example, if an ALU multiply and accumulate is 1x, reading from this very small register file locally is also going to be 1x. Reading from a neighboring processing element is going to be 2x. Reading from a buffer, shared global buffer, is going to be 6x the energy, and then going to DRAM is going to be the most expensive, right? So farther and larger memories consume more power. I think the analogy you can think about it here is that, for example, your register file could be your bag that you have with you right now. It's really cheap to reach and grab data from that. You could also grab data from your neighbor. That would be pretty cheap. You could have a global buffer, could be maybe like the bag check in this conference center. It would be a little bit more expensive to go there, but there's limited size. And then if you have to go all the way back to your hotel where you could store lots of stuff, that's going to be most expensive, right? So ideally, what you want to do is you want to maximize data reuse at the low-cost memory, meaning try and read everything as possible from this very small memory that you have very close to the processing element, right? And the main challenge, of course, is that these small memories are very small. We're talking about 1 KB of memory, but we're talking about neural nets with millions of weights and activation. So the big challenge is how do we chop up this very large neural network into small pieces, and what is the order of which we want to process each of these pieces? That's the big challenge that we're faced. And so obviously this has been widely explored for a range of different processors out there, so I'll briefly kind of give you an idea of how to think through the different approaches people have taken. So you have first what we call weight stationary, and the idea here is that I'm going to store the weights in this very small local memory, so the weights don't move. So the weight energy is reduced, but it comes at a cost of the partial sums and activations moving throughout the system between the different processing elements and from global buffer. Common architectures that use this include the TPU from Google and NVDLA from NVIDIA. Another strategy is to say, well, weights I only read, but partial sums I'm going to read and write. So maybe I should hold the partial sums locally in that local memory. We call this output stationary because the partial sums accumulate to the output. But this comes at a cost of the activations and the weights moving around. And so there's been various different research papers that have also used this approach. And then finally, another approach is using what we call input stationary, and they say basically forget about the weights and forget about partial sums. I'm going to put the input locally in my local storage. And SCNN, which is another processor from NVIDIA and from the research team, also uses this particular approach. Another approach that you could say is that let's forget about just focusing on one particular data type. Why don't we mix the different data types that can be stored locally within the memory itself? So an approach, this is from our group, is looking at row stationary data flow. So within each processing element, you're going to exploit 1D convolutional reuse between a row of the filters and a row of the feature maps. And then also the accumulation for that 1D convolution, the partial sum accumulation is also going to allow for reuse within that register file. And so this is just for 1D, and then you can expand row stationary to 2D and multiple dimensions with multiple PEs together. I won't go into the details of this given the limitation in terms of time, but the key idea here is that rather than focusing on one particular data type, so rather than saying I'm going to reduce weight energy or input energy or output energy, it's more important to reduce overall energy costs, and so you should balance the cost of all the different data types and minimize overall energy, and that's really what row stationary is trying to achieve. Just to, again, show the impact of building specialized hardware compared to general purpose processors. So we did realize row stationary in the Iris chip. This was published back in 2016. And using the row stationary data flow, we can exploit a lot of data reuse. So you reduce the number of memory accesses from the global buffer by 100x, and then reduce the memory access from off-chip DRAM by over 1,000x. And so when you compare it to a mobile GPU, it's an order of magnitude more energy efficient. And this is because it's really trying to focus on reducing the data movement itself. Okay. So these are the various architectures that you can kind of exploit or methods you can exploit to make your architecture more energy efficient. If we take a step back before the break, just a step back is looking at, let's say I don't care about hardware, and all I really care about from a systems point of view is the trade-off between energy and accuracy, right? So shown here is a plot. On the x-axis, it's the accuracy. On the y-axis, it's going to be the energy consumption, and this is for an object detection task. And we've measured, so you can see the energy for various different approaches to object detection for various different features. So you can use the hog-based approach, which was popular before all this neural network stuff kicked back up. And then you have AlexNet and VGG, for example. And you can see that obviously neural networks doubles or triples the accuracy that you can achieve, and that's why we're very excited here. But what's also interesting is to look on the vertical axis, right? And this is basically the energy that's consumed per pixel, and this is on the exponential scale. You can see that, okay, just as a reference, video compression is around 1 nanojoule per pixel. And the reason I use video compression as a baseline is because you all have video compression on your phone. If we really want to move neural networks to the phone itself or make it as ubiquitous as video compression, this is kind of the mark we want to hit. And you can see that with histogram of oriented features, and I wanted to say the energy measurements here are from specialized hardware that we actually built within our group, so it's kind of, and the two students spent about similar amount of time optimizing these two chips, so it's kind of as a controlled experiment as we could make it. But anyways, you can see with a hog-based approach, which is based on this chip here, you can actually consume less energy per pixel than you would in video compression, which is pretty exciting, meaning for the same energy, I can actually understand the video as compressing the video. But when we look at neural network approaches, you're talking about 2 to 3 orders of magnitude increase in energy consumption to achieve that increase in accuracy. So one way to think about this is if I told you that I could double the accuracy of whatever vision algorithms that's running on your phone, but it's going to cost your battery life 300 times or 10,000 times, it's going to make your battery drain that much faster. Would you be interested in that? Right? So this is just really emphasizing that energy, if you really want to widely deploy this technology, it's really important to further reduce the energy consumption. And this is already with specialized hardware. So there definitely needs to be more that we need to do to bring down the energy costs here. And that's really what co-design is going to allow us to do. So with that, I'll take like a quick 5-minute break, and then we're going to talk about co-design in 5 minutes. If you have any questions, we can also address those right now within the 5 minutes.
Hello? Hello?
Yeah.
I have right here. Yeah.
Okay. There, okay, got it.
So, you talked about flexibility as being an important component in measuring how good of hardware is. What are some metrics that you would suggest to make sure the flexibility of the hardware, in particular as we need to develop hardware that takes into account dynamic models or graph neural networks or all the new reinforcement learning type of models? What do you suggest a good metric for flexibility?
Yeah, that's a great question. So basically, what do you suggest in terms of how to address the challenges with flexibility to support a wide range of models? We're going to talk about that in the second half, but generally speaking, I mean, it is an open challenge because every single time you add more flexibility to the hardware, there's going to be a lot more overhead, right? So how do you minimize that overhead while supporting these new different workloads? So it's understanding, what are the key properties of the maybe future workloads you might want to support, and is there a way to support that without introducing too much additional cost?
Yeah, and what type of metric could we come up with to measure the flexibility?
I think the first thing would be to have like a more diverse set of workloads that you evaluate a given platform for, right? So you could imagine just saying not just limiting the reporting accuracy throughput, latency, energy costs just for a limited data set, but for a wide range of data sets, or reporting it for the extremes of what the processor could actually support.
Thank you.
Yep.
Yeah.
Okay, maybe you can ask, I'll repeat it.
So here or there? Okay, I go ahead. Thanks for the presentation so far. How do you think about neuromorphic chips?
Okay, so I'll answer her question now. So she was asking about FPGAs. We'll talk about it very briefly after the break. But it faces a lot of similar challenges as the hardware design.
Yeah, so, decision makers like to do executive math. And you've been describing this very high-dimensional space of different trade-offs. I was wondering what you think about simple benchmarks like MLPerf. Are they too simple to be useful?
No, so it's a great question. Maybe I shouldn't have stopped for a break. I'll talk about that right after the break in terms of MLPerf and those benchmarks. I think it's definitely useful to have some standard benchmarks. I think it's also important to think through for your particular applications, what are the requirements that you might have. It might be different from the MLPerf benchmark. It really depends on your use case. It makes a difference if you're doing processing on an edge device like an IoT device versus in the cloud in the data center. Right? These would have very different workloads that you need to support and characteristics or limitations in terms of power, speed, and so on that you would have.
Yeah. So the problem is that executives don't do that complicated nuance. Right.
Correct. I'm always a little bit concerned about rather than just coming up like a figure of merit where you combine all the metrics together. I don't think that reveals a lot of the trade-offs that are really important when you're trying to evaluate if this is the right solution for your particular application. Okay. With the interest of time, I'll take the next questions after the end of the tutorial. So let's just get back into it. So we're going to talk about co-design. So maybe this is going to align a little bit more with the audience here, which is that we know that even with all the specialized hardware that we've looked at and people have been working on, we still have this huge energy gap that we need to overcome in order to achieve efficient processing. So how can we do that from both an algorithm and a hardware example approach? And the idea here is that when you want to do co-design, the hope is that by changing the algorithm and the hardware together, you could do better than just each of these on its own. Okay? Generally speaking, the co-design approaches can be loosely grouped into two categories. You can be looking at reducing the size of each operand, which would reduce the storage and compute costs. So this is often, reduced precision is a good example of this. You could also look at reducing the number of operands that you might have, which again will reduce storage and compute costs. And this often is involving things like sparsity and efficient network architectures. Again, I think I want to really reiterate here is that although you can apply these particular approaches without changing the hardware, if you really want to achieve increased savings in terms of both energy and latency, often you need to have specialized hardware support to do this. And then the key thing is to ensure that the overhead of the hardware is not going to exceed the benefits. And we'll see some examples of that. And then unlike the previous stuff that we discussed before the break itself, all of these approaches will affect accuracy. So it's important to look at the trade-off between accuracy and the other metrics. All right, so let's start with reduced precision. So why do we want to reduce precision? Right, so if you can reduce precision, obviously you can reduce the data movement and the storage cost of the inputs and the outputs of the Mac itself. We know that smaller memories tend to consume lower energy as well. So if you can reduce the memory size, reduce the cost and the energy consumption. You also want to reduce the cost of the Mac. So the cost of the multiply, for example, is going to scale with bit width. So the energy and area is going to scale quadratically with the bit width. So here's a hardware of a multiplier. You can see it scales quadratically with the bit width of the two inputs. And then delay is going to scale linearly. Another thing I just want to emphasize is the bit width of the multiplication and accumulation are often different. So for example, you can have a 8-bit bit width for your multiply, but your accumulate might still be 32 bits. It really depends on how many items it has to accumulate, which is often dictated by the number of weights in your filter, your max filter size. Again, we already showed this before, but this is just showing the kind of the linear relationship, quadratic relationship in terms of energy and area with respect to precision for a multiply, and it's a more linear relationship for addition or accumulation itself. What really determines the bit width? Right, so shown here on the right-hand side are some examples of very common numerical representations like floating point 32, 16-bit floating point, and like integer 8 and 16 and so on. So the first thing that dictates the bit width is the number of unique values we might want to represent. So we would refer to this as like the mantissa or the m bits, and it can represent, with m bits you can represent 2 to the m values, right? So we're showing here's m. There's also the dynamic range of the values that you also want to support, right? So for example, with the exponent, the e-bits, with e-bits you can scale the values by 2 to the e, basically. And so we can see for floating point, we often have these e-bits. And then if you're signed or unsigned, if you're signed, you're going to add an extra bit for the sign itself. So for the total bits is a summation of all these like sign bit, exponent bits, and mantissa, so s plus e plus m. For floating point, you allow for the range or dynamic range to change for each value, so you have to include e-bits into your actual number. Whereas for fixed point, you often fix the range, so for these integer values which are fixed point, they don't have the e-bits themselves. And then the default for CPUs and GPUs is 32-bit float. Okay? So what determines the bit width? Well, it also, for an accuracy point of view, it really depends. What you're trying to do is have sufficient precision to represent the various different data types, right? So for inference, you have the weight data, the activation data, and partial sums. Whereas for training, in addition to weights, activation, partial sums, you also have gradients and weight update. Right? And often these gradients of weight update will require higher precision, which we'll talk about. But in general, if you're going to have different precisions across the different data types, this is often what is referred to as mixed precision. So if you hear the term mixed precision, it's referring to having different data types for these different precisions for these different data types. So what are the strategies that people take in order to reduce the bit width? So one is reduce the number of unique values, and this is really reducing the m bits. Right? So the default that's typically used is first uniform quantization, which means that each of the levels are equally spaced, or each of the values that can be represented are equally spaced out. But you can see if, like, let's say we're looking at a weight distribution, that the weights are not all equally spaced out. So drawing these lines in equal spacing might not be the most efficient way to use your unique values. A better way might be using non-uniform quantization. So for example, you can have logarithmic quantization, which is shown here for lognet. So you have a logarithmic spacing of your different lines. And in particular, if you're spacing it relative to the power of 2, then your multiplication can be implemented as a shift, because anything times 2 is going to, or power of 2 is going to be shifts. So that would be one case. So this could be, the spacing can be computed if you're using logarithmic, or if you're going to use some learned spacing, you're going to have to use a lookup table itself. The other thing to point out is that you have fewer unique weights, and this is actually going to make it more things like transforms and compression more effective. So there's the benefit of doing this. You can also reduce the dynamic range itself. So this is reducing the e-bits. So if possible, and if you can use just a fixed range, then you can use fixed point. You don't need any e-bits. Or another strategy people take is that they cluster values together. So they can share the same range or same bits. And so this, you can imagine like the weights of the same layer are going to have the same range, or the weights from the same channel, and so on. And then often there's going to be a trade-off between the bits allocated to, m bits, the mantissa, or e bits, the exponent. So for example, where we've most recently seen this is the representation of 16-bit floating point. If you take the IEEE standard, it's doing 1 sign bit, 5 exponent bits, and 10 mantissa bits, right? So it gives a range between basically e to the -8 and e to the 4. But then there's been this new B-float-based approach, which basically allocates more of the bits towards the exponent, which is the range, as opposed to the number of unique values, which is the mantissa. And so they get a much wider range from e to the -38 to e to the 38. And then both of these are used in training. And so in terms of the reduced precision, commercial products already use reduced precision for various, both inference and training. So for example, a very standard thing now is that for inference, 8-bit fixed point is used, or 8-bit integer, and for training, 16-bit float is used, right? So rather than using the 32-bit float, these are pretty standard now in commercial products. From the research point of view, obviously there's a push to be even more aggressive. So if we can imagine using things like binary nets, using only one bit for the weights, and so your filters would look, basically black and white because they're binary. You can still look at reducing the number of unique weights and activations. In this case, you might add a scaling factor depending on the layer or the spatial position within the activation itself. We talked about nonlinear quantization. That's also being explored. And then from training, there's been research showing you could also do 8-bit with stochastic rounding. Okay, so these are all kind of more researchy things that people are going to try to push the precision for the reasons we talked about before. The one thing I want to highlight is that if the precision changes from layer to layer or from different data types, you often need to have hardware to support that, right? So a very typical thing to do from a hardware perspective is to basically gate or turn off those, the parts of the multiplier that are not going to be used if you go from, let's say, 8-bit down to 4-bit or 2-bit. Right, and this is going to really reduce the energy consumption. But the problem is if you're going to shut all these or gate all these things off, it seems like a lot of wasted hardware. You already put the transistors down. Can we use those to actually increase the throughput instead? So there's been a lot of research in the hardware community trying to figure out, can we, better utilize these full adders? Can we add additional logic so that rather than, let's say, doing, one 4x4, we can do, 2 4x4s or 4 4x4s for using the same logic that was put down for the 8x8 itself. And so this basically is trying to look at, can we, increase the utilization of the hardware so that it can have higher throughput per area. But as it turns out, the cost of adding all this logic, you can see here that this, flexible multiplier is going to be much more expensive or much more complicated than these other ones. And it turns out all the hardware that you add in order to try and utilize all that other logic actually can introduce a lot of overhead. So for example, in this particular paper that studies like 19 different precision scaling Mac designs, they show that if 95% of your workload is 2x2 and 4x4, but only 5% of your workload is 8x8, the overhead that you've introduced in order to support those lower precisions is so significant when you process the 8x8 that at most you can get maybe a 1.3x improvement in energy and a 1.6x improvement in throughput per area because of the overhead of introducing this flexibility. Right, so this is still kind of an open problem, but important to think about every single time you want to support something special. It often requires some additional hardware, and that can have additional energy and area costs. So things to think about for reduced precision. First, it's really important to, again, consider the impact of accuracy, in particular on the difficulty of the dataset task or DNN model. It might be really easy to do, binary or reduced precision for things like digit classification, but the question is whether or not it applies to more difficult tasks. We saw, does the hardware actually exceed the benefits? We saw that there's a lot of overhead for supporting variable precision, so all this additional shift and add logic and registers. The granularity also has an impact, in both in terms of overhead and in terms of accuracy. So, if you want to support, 1-bit, 2-bit, 3-bit, all the way up to 16-bit, that's going to be much more expensive than doing like 2-bit, 4-bit, 8-bit, 16-bits, right? So you really have to decide, is it worthwhile in terms of accuracy gain to support all this fine granularity, because there's a lot of area and energy overhead to do that. And then finally, in terms of evaluation, it's really, we saw that commercially there's already 8-bit for inference and 16-bit for floating points for inference and training. Those pretty much should be used for baseline. A 32-bit floating point would be a very weak baseline to use. Okay? So these are all things to keep in mind when evaluating approaches. Let's talk about sparsity. So why increase sparsity? So we already hinted towards this. We want to reduce the number of max. So anything multiplied by 0 is going to be 0. So if you can avoid performing unnecessary max, that would be great if you can recognize that one of the inputs are 0, and obviously can also reduce energy consumption and latency. You can also reduce data movement, so if one of the inputs to the Mac is going to be 0, that means you don't even have to fetch the other input to the Mac. Also, if you have a bunch of zeros, you can also compress the data and only send the non-zero values, and that's going to reduce data movement. In GPUs and CPUs, they often have libraries to support sparsity, but it often requires really high sparsity, like above 99%, because of the overhead to support sparsity. And for DNNs, typically the sparsity is going to be lower than that, so you often need to have specialized hardware to see these gains. So where does the sparsity come from? So there's some natural places where sparsity will happen. In the activation, if you use a ReLU, basically you set all negative values to 0, so automatically you're going to generate a bunch of zeros in your activations. So for example, if we look at the different layers of, let's say, AlexNet, these are the activations. Blue is the number of activations, and then red is the number of non-zero activations. And you can see that the number of non-zero activations is significantly lower than the total activation. So in fact, if you look at like layer 5 there, like 75% of the activations are 0. And so how can we exploit this? There's two typical ways people do it. One is you can gate the operation. So this is basically saying don't do the multiplication and accumulate if one of the inputs are 0. Specifically, the activation is 0, right? And this can actually save you 45% in terms of the power consumption. This also says don't fetch the other input operand if the activation is 0. But this doesn't actually, gating the operation doesn't actually save you any cycles. Another approach to increase throughput is just to say, in addition to just not doing anything, why don't you just take this cycle to do the next multiplication? So save cycles, and then you can increase throughput, and they were able to show, up to a 1.8x increase in terms of throughput. This is in the Convolution work. Another approach is to compress the data. So if you have a bunch of zeros, we can think of using things like run length encoding, where rather than sending all the zeros, you're just going to send the run length of the zeros. This is a very simple form of compression, right? So rather than sending, let's say, like 4 zeros here, you're going to send the number 4 and just say there's a run length of 4. And by applying this kind of compression, you can get potentially up to 2x reduction in terms of data movement. In the case of Iris, this was applied for DRAM access because that often is very expensive. So this is in the activation side where you naturally get to zeros. In the weight side of things, you can actually force getting zeros. So for example, this is actually, and this is forcing zeros or removing weights and sending them to zeros, often referred to as pruning, and this has been explored, since the early days of neural nets. So Jan LeCun had a paper on optimal brain damage, which is just basically saying removing, sending these weights to zeros, and then adding some retraining, and you can restore the accuracy despite having removed some of the weights. And then in the deep compression work, they've applied this to modern DNNs, and in particular for the AlexNet case, they were able to show, in the fully connected layers, a significant removal of weights. So you can reduce the number of weights in the fully connected layers by almost 10x. In terms of how to remove the weights, it also is important to figure out the coarseness of the sparsity, whether it's what we call it unstructured or structured sparsity. So you can imagine if you can remove weights anywhere in any location, we would call that fine-grained sparsity. That would be very irregular. Or you can constrain it so that you can only remove like rows of weights or specific filters or specific channels or specific filters to remove the weights. And the reason why this matters is as you increase the coarseness, so moving from left to right, as you add more structure, it's much easier for the hardware to exploit this. There's much less overhead for the hardware because it doesn't have to go and find every possible location of the non-zeros. It knows like this whole cluster is going to be 0. I just skipped like this whole entire region. And then also in terms of compression, the signaling overhead to signal where the non-zero values are going to be is also going to be more efficient. You can compress better if you have coarser sparsity. So the overhead of the signaling the location of the non-zero is lower and you get better compression. The main challenge, of course, is that as you increase the coarseness, your accuracy is going to be harder to maintain. Okay, so this is a trade-off in terms of accuracy and, again, the overhead of the hardware and compression. So again, very similar to in reduced precision. For sparsity point of view, again, you should consider the data set, task, and DNN model when you're considering accuracy. We know that AlexNet and VGG are very overly parameterized, so they're easy to prune. If you looked at a much more compact model, could you still be able to, or efficient model, could you still be able to remove the weights? Does the hardware cost exceed the benefits? We often need to add extra hardware to identify the locations of the sparsity. And location of the non-zero values. We also, if you have a design that wants to account for both the sparsity and both the weights and activations, that's going to also be very expensive and challenging because you need to find the intersection between these two streams. As opposed to if you just did activations or just did weights alone, you just have to find where's the next non-zero location within this one stream. But if you have to look at both data types, it's going to be much more challenging. Again, we just talked about the coarseness and granularity. That has a big impact in terms of hardware overhead and accuracy. And then once you compress data, normally it becomes what we call variable length. So this reduces the flexibility we have in terms of accessing the data. So in terms of random access, it's going to be very, very expensive. Okay, so these are all the different trade-offs from a sparsity point of view. The last thing we want to talk about in terms of the co-design is also looking at efficient network architectures. Right? So more recently, people have been looking at how can we make the network architecture itself, so the filter shapes, more efficient. This tends to increase the variation in the various different filter shapes, so this will have implications from the hardware point of view. And this can actually be done either in a manual handcrafted way or using an automated way, so for example, neural architecture search or NAS. Right? So some typical examples of this is if you decompose a filter, you can build a large filter from smaller filters, or you can add these one-by-one convolutions to reduce the number of channels before performing a large filter. And you can see here by these, using these approaches, let's say AlexNet and MobileNet, you can see that even though MobileNet has higher accuracy than AlexNet, it has significantly fewer weights and max, right? Very briefly, in terms of the different manual design approaches people take, often they focus on reducing the dimensions of the filters themselves. So you can reduce spatial size, channel size, reduce number of filters, and layer pooling. So I'll just briefly walk through each of these. In terms of reducing the spatial size, so that's the R and S dimensions of the filter itself, you can basically take one filter and decompose and have two stacked filters, or smaller filters that stack together and have the effective impact of that one large filter. So for example, GoogleNet and Inception, they decompose a 5x5 into 1x5 and 5x1. These are like basically separable filters, and then they apply them one at a time. I would say that this approach is very well known in the image processing community. We often separate the dimensions. VGG also decomposes a 5x5 filter into two 3x3 filters and then stacks them. You can also apply one-by-one convolution. So the goal of the one-by-one convolution is basically to summarize the cross-channel information, and you can reduce the number of channels before you do convolution on them. So for example, let me just run through this quickly. If each of these were applying one-by-one, you can see the spatial support, R and S don't change, but the number of channels change. So for example, you can go from 64 channels to 32 channels by applying 32 one-by-one convolutions on this particular input. An example of some work that actually uses this would be GoogleNet, for example. They do these one-by-one convolutions before every quote-unquote larger filter convolutions. So that's basically reducing the R and S. Another thing, and the number of channels. Another thing you can do to reduce the number of channels is called group of filters, right? So rather than have each filter have the same number of channels as your input feature map, you can reduce the number of channels in your filter. So for example, if we half the number of filters in our channel, we're going to basically divide our filters into two groups, right? So filter one will basically process the first half of the channels in the input feature map, and filter two will process the second half of the channels in the input feature map. We are actually going to be able to reduce the number of weights and multiplications by 2x. Okay? And you can take this to the extreme, where basically each filter only processes one channel of the input feature map. And this is basically what we would call depth-wise convolution. This has been widely explored. This is very much the extreme of this. So this is used in things like MobileNet and ShuffleNet. And then the key idea here is that once you do these channel groups, the problem is that you still want to attain information across channels. So how can you mix the information across channels? So in the MobileNet case, we have a one-by-one or point-wise convolution that allows you to mix the information across channels after applying these depth-wise filters. And in ShuffleNet, they mix it across different layers. So after you aggregate across different layers, you've mixed kind of the channel information across different channels. Another thing you can do is try and reduce the number of filters by exploiting what we call feature map reuse. Right? So let's say you have a layer, like layer 3 here has M channels. So typically to generate M channels, you're going to have to apply M filters to the input feature map. Instead, what you can do is you can pull some of those feature maps, some of those channels from previous layers across. So let's say we take M minus K layers or channels from previous layers. Then that means that I only need to apply K filters to this input feature map to generate an output of M channels. Okay, and where is this widely applied? Well, DenseNet uses this very widely across many layers. Finally, you have what we call layer pooling, and this is typically used to simplify the fully connected layer. So if you think back all the way to AlexNet, for example, typically the first fully connected layer has a significant portion of the weight. So in AlexNet, it accounts for 38 million of the total 61 million weights. And so what you can do to reduce the cost of this first fully connected layer is apply what we call global pooling. So rather than basically multiplying all the weights and all the filters with all the activations input feature map, what you can do is you can do global pooling. So you're basically pooling each of the channels of the input feature map into one value. So basically you reduce the spatial, basically you're summarizing this from a spatial perspective of the amount of data there, and so then you significantly reduce the cost of the fully connected layer that would come after this. So, for example, in this example, rather than having H times W times C times 1,000, assuming you have 1,000 classes, you've set the H and W to 1, right? So your savings is a factor of H by W. So these are, like, generally speaking, the types of manual network design approaches people have taken. But of course, you can automate this whole thing and use machine learning design neural architectures, and that's basically what this NAS stuff is doing. The idea is that you automate this whole process. In NAS, there's basically three main components to think of. So one is, what is the search space of all possible networks that you're going to explore? So what are the set of samples you want to explore? What is the optimization algorithm, which is basically going to tell you, which samples to actually explore within that space? Like, how do you decide what to sample? What's the next location to go? And then also you have performance evaluation. So once I sample a given architecture, how can I evaluate its accuracy and its speed if I'm caring about speed itself? And so you can imagine this is a very iterative approach. You would repeat these three components many times, and eventually you would converge on a final network. In terms of evaluating these NAS approaches, what you really want to think about is both the accuracy and the search time. These are the two kind of key components. So what is the achievable accuracy of these algorithms and the search time of these algorithms? In terms of search times, there's a couple of key components. You can imagine that NAS time is a product of the number of samples that you're going to take and then the time you spend per sample. Right? This seems very logical. In terms of this, you can break it down further for those three components. So, for example, in terms of the number of samples, there's, first there's the size of the search space itself. So if you can shrink the search space, if you don't search as many samples, obviously the number of samples is going to reduce. In terms of your optimization algorithm, there's two contributions in terms of the time. So it depends on how easy it is to tune your algorithm. If your optimization algorithm is difficult to tune, you might have to repeat the tuning multiple times. And then there's an aspect of how smart or how efficient your optimization algorithm is once you have it tuned, in terms of how many steps it takes to find the best sample itself. So those two both affect the result. And you can imagine in some cases there might be a trade-off between the difficulty of tuning and how quickly it can actually find the best architecture. And then once you've found an architecture, what is the cost of both training that architecture and then evaluating the accuracy of that architecture or its performance itself? So all these factors really affect the overall search time. And when we look at all this exciting work in the NAS space, it's all about improving these three components. Very briefly about in terms of the search space. So if you have an architecture universe, which is anything, what you want to do is you kind of trade off the breadth of the architectures you can search for the search space. So you shrink it down. So if you can, if you reduce the search space and you only sample in the search space, that's great. And if the optimals were still within that search space, that's fantastic. But there could be an issue where the optimal design is actually outside of your search space. And then in that case, you'll never be able to find it regardless of how good your optimization algorithm may be. So that can be an issue. Usually in order to design the search space, people rely on domain knowledge from manual network design to help guide what it should be. So one example of this is somewhere from CVPR back in 2018. So they basically defined a set of common layer operations. So this was the search space itself. That's the layer operation part of the search space. And then the other is you can also define the connections between the layers. You can be, shown here on the left, is the most flexible, any possible connection. Or you can basically say, I'm going to have fixed connection between different blocks and then just search within, basically search the architecture for each block. And then have predefined connections. Everything's fixed. And then I just search the, what should the dimension of the layers be with this fixed connection. In terms of optimization algorithms, again, there's many that are out there, and typically I won't go through the details, but there's typically a trade-off between, the flexibility of these algorithms, the speed of them, how easy they are to use, and the quality of results. Right? And these are different ways of how you might use them. The flexibility refers to basically how these optimization algorithms might be combined with, different search spaces and so on. There might be some limitation there. And then finally, in terms of simplifying the performance evaluation, really what you're trying to do when you search this space is you're trying to rank all the different possibilities of your neural architecture, like of the samples that you have. And so there's different ways that you could speed up the evaluation, because you don't necessarily need to know the absolute accuracy, you just need to know the rank of which one's just doing better or which one's just doing faster. So some ways that people do it are they have a proxy task, so they might have a simpler task, or they train on a simpler data set. You might have what we call early termination, which basically means that you don't train all the way through, you might stop early, or you might try to extrapolate and predict what the accuracy might be, so you don't have to train all the way through. Another approach that people take is that they use information from previously trained networks to estimate what the weights would be of the current network. So for example, it might just copy some weights over from like a previously selected larger network, or it might, from a previous network, the previous network generates some kind of feature map, and then so it figures out what are the weights in the new network that could generate an equivalent feature map. So it uses basically some hints from a previous network so that it doesn't have to fully train the new network or guide the training of the fully new network. Finally, if you care about things like metrics like, latency or efficiency, you might use approximate metrics. So rather than, let's say, measuring the latency, it might look at the number of MACs to estimate latency, or it might have some lookup tables in terms of what the latency could be for different filters and different channels, and combine these lookup tables for different layers to estimate the latency of the overall system. So what are some design considerations for the NAS themselves? So the first thing is that it's important to realize that the components can't be selected individually. So for example, some optimization algorithms might limit the search space. And for example, the type of metrics that you might use to drive the optimization algorithms might also limit the optimization algorithm. So for example, if you use a metric that's not differentiable, maybe you can't use gradient descent. Some other important things to consider when evaluating these different NAS algorithms. First is obviously the complexity of the implementation is really hard to implement. It might be a challenge. The ease of tuning the hyperparameters for the optimization. So are there a lot of hyperparameters? Are they easy to tune? That can also impact the usability of it. And then also the probability of convergence to a good architecture, right? So if, person A designs this NAS, can, person C, B and C also still achieve the same accuracy as person one? Was it just luck that they hit something that was very accurate, or is it the probability pretty high that it would also find a good network architecture if it was used multiple times? One thing in all of these co-design things that we should really keep into account is bringing hardware in the loop. And the reason for this is that when we start evaluating the complexity of the DNN models, the easiest thing to do is, basically count the number of MACs and count the number of weights. But it's actually been shown that the number of MACs and weights are not very good proxies for things like latency and energy. So for example, the mobile vision team at Google has shown that the number of operations is not a good way to approximate latency. So for example, for the same number of MACs, you can have a 2x swing in terms of latency, and for the same amount of latency, you can get a 3x swing in terms of MACs. Similarly, in some of our own research, we've also seen that looking at weights alone is not necessarily a good metric for energy consumption. In fact, all data types should be considered. This is very similar to the data flow stuff that we discussed before. So if we look down at the breakdown of the energy consumption of GoogleNet, we can see that the weights only account for 22% of the overall energy, but feature map movement also accounts for a significant portion of the energy consumption. And this was all estimated using the energy estimation tool on our website. And so once you have an idea in terms of the energy and latency metrics, you can actually incorporate them directly into the design of your neural network. So for example, rather than removing weights based on the magnitude, we call this magnitude-based pruning. Typically, people remove weights that are small magnitude. If you can remove the weights that consume the most energy, then you can often get a better trade-off in terms of accuracy versus energy cost. So in energy-aware pruning, which is just one example of how to do it, what we do is we sort the layers of the neural net based on highest energy to lowest energy, and then prune the high layer energy layers first. And so you know there's a kind of a trade-off between number of weights you remove and the accuracy. And so if you prune the high energy layers first, then you likely were pruning the weights that consume the most energy first. And then you get about a 1.7x better performance compared to magnitude-based pruning for the same accuracy. And this is just really further motivating that you should really take energy into account when you're designing these neural nets. Another example is NetAdapt, which is basically a kind of a NAS approach to automatically adapt a DNN for a given mobile platform for a target latency and energy budget. And it's really driven by empirical measurements of the actual neural net on a mobile platform itself. Basically what it does is it starts with a pre-trained network, it generates a bunch of proposals, measures these proposals on the platform, and then feeds that back in. It'll iterate this until it hits a given target energy or latency budget. The nice thing about this algorithm is it requires very few hyperparameters to tune, and then all the code is available on the project website. And just to kind of show the impact of this compared to manual design, so on the x-axis is the latency, and on the y-axis is accuracy, so upper to the left is better. And we can see NetAdapt is shown here in the red. And so when you compare it to handcrafted based approaches for MobileNet and MorphNet, you can see that it achieves higher or lower latency, but 1.47x faster at around the same amount of accuracy. And this, I should mention, this is for a very small, the smallest mobile net. So even for a small mobile net, by factoring in latency directly into the design of the neural net, you can achieve much higher performance. Okay, so what are the key takeaways or design considerations for the co-design approach? There's the impact on accuracy, so you want to consider the quality of the baseline, right, of the DNN model. And often you might want to also sweep the curve of accuracy versus these various different metrics so you can see the full trade-off. Again, we always want to talk about whether or not the hardware cost exceeds the benefit of the given approach, because often all these approaches need additional hardware, and the granularity of how well you want to adapt also matters. And then for an evaluation, you want to avoid only evaluating on things like weights and max. Instead, you want to really factor in real metrics that we care from a hardware point of view, like energy and latency. Some other things to factor in also is the time required to perform the co-design. So there's many different methods out there, but with things that we want to also figure out to get to the final result is like, for example, is it difficult to tune the algorithms to make it to work? Do they have what are the number of hyperparameters, or the relationship between the hyperparameters and the impact of performance? Does that have a clear relationship? All of these things affect how easy it is to use the co-design approach. We should also factor in, when we're comparing different approaches, other aspects of the system which will also affect accuracy, right? So for example, things like data augmentation pre-processing affect accuracy, latency, and energy. The optimization algorithm, hyperparameters, learning rate, batch size also affect. Training and tuning time, so if you have one particular design that's been trained or tuned for a long period of time compared to another one that hasn't, then obviously there's going to be a discrepancy there. And also the type of, the library that's being used and the quality of code also affected. So these are things that ideally you'd all hold constant when you're comparing various different co-design techniques. And then finally, we should often ask, does the co-design approach apply for different platforms? Or is it very specific? Is it a general method, or is it very specific for a given piece of hardware itself? Finally, in terms of the training approaches for co-design, there's two kind of approaches people take. One is you train from scratch, right? The other is you use a pre-trained large model already and you try and simplify it down, right? So for example, you can use the weights from the pre-trained model to initialize the weights on the efficient DNN model. Or you can do things like knowledge distillation, where you train a bunch of models and you try and match, their scores or their probabilities. And here you would actually have to keep your trained model around. So I always like to explain, the knowledge distillation is very similar to what we're doing here. So you have us that we've trained and looked at all these papers for all these years, and I'm trying to distill it down to you guys, which is the more efficient way of learning. The key question here is, which one is better to use? There's no guarantee as to which approach is better. I think that's still an open area of research. Okay, so in the interest of time, I'll just briefly talk about flexibility and scalability. I won't go too much into the details, but we know that there's all these approaches, and ideally, you have hardware that can support all of it because you have no guarantee as to which approach people will use. I think the main challenge in existing processors is that they often design the DNN processors to exploit certain properties of the DNN. For example, they assume that like a typical design is going to be an array of max, and then they have like weight reuse on the, let's say, the row dimension and activation reuse on the vertical dimension. And this is good because we want to reduce data movement. But then the amount of reuse you have in each of these dimensions really depends on the dimensions of your neural net itself. And so this was great when you had these very large neural networks, which you have a lot of reuse in like each of the, the number of weights per filter and so on, or number of input channels and so on. But when you start looking at more efficient neural network architectures, like depth-wise layers where there's only one input channel, then you actually start becoming very inefficient in your hardware, right? You can't really utilize all the Ps and exploit all that reuse. One way to get around this is to have a more flexible hardware, so you have more flexible data flow, for example, and row stationary can be a flexible data flow. The other thing is the on-chip network, which is basically delivering data from your global buffer to the rest of the processing elements. That also has to be very flexible. At one extreme, when you have very large neural networks, you want to have kind of a broadcast type of network that exploits reuse. But on the other hand, when you have these really compact neural nets, or more very efficient neural nets with very low reuse, you want to have more of a unicast, high bandwidth based approach. And if you use just like an all-to-all network that satisfies this whole range, it's not going to be very scalable. I'm just going to skip this, but there's a way that you can do this with a hierarchical mesh, which was explored in the second version of Iris. But the key thing is that if you can have a much more flexible data flow, you can support a wide range of filter shapes. You can support both dense and sparse neural nets. One key thing is when you add flexibility, you want to make sure that the design can still scale up. So if I'm going to give you more processing elements, can you still run faster and make use of those processing elements? And so by kind of factoring in efficiency and flexibility together, you can often achieve better better efficiency and speed compared to not taking that stuff in. All right, so because we got questions about flexibility, so there's many existing DNN processors. As I mentioned, they often rely on certain properties of the DNN itself. But the problem is that we have so many different DNN models these days. So when you're kind of evaluating a given processor, you really want to see how it performs on this wide range of DNNs. There was a question about benchmarking. So again, it's really important to evaluate DNNs on a wide range of benchmarks, and MLPerf, this new benchmark that came out over the past 2 years, is a great way to start evaluating DNNs on a processor on a wide range of workloads. But you might need more depending on your application. So if you need to look at things like reduced precision, sparsity, efficient networks, you might have to look beyond that. I know MLPerf is also growing beyond the first version to encompass more. And scalability is also important, because if I'm going to scale up my architecture, if I add more resources, I want to go faster or be more efficient. And there's been good examples about doing that over the past few years in terms of people are, for example, combining multiple chips together and to form one big neural network processor, or even doing things like wafer scaling where the processor can take up the entire wafer itself. All right, so finally, to summarize just for ASICs, the things that we want to think about is like reducing the PE utilization. So you want flexible mapping and on-chip networks so that you can utilize all the hardware, but this often needs additional hardware to support. We want to reduce data movement, so we talked about efficient data flows and memory hierarchies to exploit data reuse. You might also want to apply compression to reduce the data movement, but this also requires additional hardware. You can reduce the time and energy per MAC. This often involves things like reducing precision. If the precision varies, you're going to need additional hardware to support that, and it also has impact on accuracy. And then, of course, reducing unnecessary MACs, so you want to exploit sparsity. So you want to need additional hardware again, impact in terms of accuracy. You also want to avoid redundant operation by using things like transforms, but this requires additional hardware. There are other more exotic platforms that exist these days that people are looking at. So we talked about the fact that data movement's expensive. So what people are also looking at is how can I, rather than moving the data to the compute, can I move the compute to the data itself? So this is this whole phenomenon of like processing in memory, this whole area of research doing that. Really what they're doing though is when you move the processing into the compute, you often have to use analog computing. And so as a result, there's a lot of kind of circuit and device level challenges there, because then you're going to be much more sensitive to the non-idealities of the circuits, of the devices and so on. I don't have time to get too much into this, but there's a tutorial that we're running at ISSCC, which is more of a circuits conference in February. So if you're interested in this, I would invite you to attend that, or also look at these reference papers that cover this. FPGAs is another platform people have been using a lot. Often they're implementing the matrix vector multiplication operation, so Brainwave from Microsoft has done that. This is a weight stationary-based approach, and another strategy they apply is to kind of try and reduce precision so they can fit all the weights onto the FPGA, and so you can have a batch size of 1, for low latency. And so they're showing here that if they reduce the precision, they can fit much more max and weights on chip, and then so the throughput will go up. Again, we'll discuss this more at SSCC if you're attending that. Okay, so 2 last things. So one is that obviously there's a huge, if you get anything out of this tutorial, is that there's a huge number of DNN processors that are out there. And so what's also really important is to come up with tools to evaluate all the different processors out there. And so, we need a systematic way to evaluate and compare the wide range of DNN processors. If you can do that, you can also imagine using these tools to explore the design space, right? And so one way of doing this from an energy point of view, there's been tools like, for example, Excelergy that allows you to do early stage energy estimation at the architecture level, right? So once people say like, how many PEs I have, how many, what is the size of my memories, what is the NOC I have, can you just based on those items estimate what the energy cost is? So you don't have to go through the whole low-level chip design thing, taping out chips and so on. You can estimate at the beginning. You could also imagine this framework allowing you to plug in more exotic technologies like the processing and memory stuff to help estimate the energy. In combination with these energy estimation tools, you might need something like what we call time loop, where you can do sweeping and looking at the various possible data flows or different ways to map the algorithm onto this hardware. And so all this stuff is available on the Excelergy website. But again, it's just a tool to start kind of evaluating all these different platforms. Another thing that's also been really important are compilers for the different platforms itself. So obviously GPUs and CPUs have compilers, but as you have more diverse custom hardware platforms, you'd also need more sophisticated compilers. So there's been a lot of work in terms of things like TVM and Glow from Facebook looking at how do you generate optimized code for these different hardware backends from high-level frameworks like TensorFlow, PyTorch, and so on. All right, so to summarize, DNNs are a critical component of AI, but they have very high computational cost. There's a lot of approaches to doing efficient processing, and they typically involve going across the entire stack, from the algorithms to the hardware to even devices. When considering these various different solutions, and it's important to evaluate them on the appropriate workload, right? So benchmarking is really key. And then it's also important to look at all the different metrics that exist out there, not just focusing only on accuracy, only on energy, or only on throughput, because often, as in many cases, there's the trade-offs between these various different metrics, so it's important to understand all these challenges. Okay, so this is just like a 2-hour tutorial, but there's actually a whole bunch of additional resources if you're interested in pursuing this more. So this tutorial is mostly based on a proceedings paper that we wrote back at the end of 2017, and we're actually fleshing that out into a book, so if you're interested in that topic, I invite you to go take a look at that. We also teach like a 2-day course at MIT for professionals. If you want to do a deep dive more into network architecture design, I also hardware design and algorithm design, I invite you to visit that. We've run a similar type of tutorial at different computer architecture conferences, so all those slides are available on the tutorial website. And if you're just interested in the various types of research on efficient computing, you can also visit our group website. And we'll be announcing this new resource material on either the Twitter feed or our mailing list. But anyway, so if you want to know more, I just invite you to visit these resources. So with that, I conclude my tutorial. Thank you very much.
Can I ask a question?
Yeah, go ahead.
So you already mentioned about the compiler, which can help the developer or the researchers to automatically optimize the codes. But go beyond the compilers, can you also comment on the other tool chains such as IDE or libraries, which further helps the developers or the researchers? You know, nowadays the training is much faster than before. It can be finished. Typical works can be finished in seconds or even minutes, and so that the development speed is also very important. Thank you.
Yeah, I completely agree. So like all of those types of optimizations from the software layer down are very critical in terms of enabling faster performance on these different platforms. So it's really in these solutions you have to look across the entire stack, not just at the hardware themselves.
Oh, yeah. Another question. So there is a huge tendency of reducing the size of filters, reducing the precision, etc. Do you think that in the near future it will be viable to see people just dictionary encoding typical data instead of computing everything, just having multiplication tables for typical chunks of data and doing actual computations for the rest?
Yeah, so actually people have explored that. I think from a hardware perspective, the key question is how much will it actually gain you, right? So I think these are all different, like reduce the number of unique values and then you can pre-compute some stuff, or you only have to, you pre-do the multiplication. There's only a set of products that you need to store. So I think people have explored that. The question is how much can you actually gain from that? How efficient is your hardware for supporting that, right? And how much does that limit your accuracy? So these are all open questions that people are exploring. Yeah.
Thank you for the talk. Can you put up the link to these slides that you had at the start?
Yeah, they're all going to be on our website.
Oh, they're all in the...
Yeah.
Oh, sorry, if you have to scroll back, that's okay.
It goes all the way back to 100.
Okay. Thank you.
Hi. Regarding the NAS slides,
yeah.
You'd mentioned some works to rank different architectures. They estimate the weights by seeing which weights would produce the equivalent feature maps. Was there a particular work or technique that you're referring to there?
So we also explored that in, like, for example, the energy-aware pruning. We looked at that. So, for example, we tried to ensure that the output feature map didn't change, and then allowed you to have more flexibility in terms of change. You weren't pruning just based on the magnitude, but if two weights canceled each other out and didn't affect the output, you could still remove those. So in the energy-aware pruning, we explored that, but other people also explored that as well.
Okay, thanks.
Yeah, I have just simple question.
Okay.
So, can you tell me your opinion about possibility of pruning the model from network architecture search or effective model, not VGG or AlexNet? So,
your question is, can you, with neural architecture search, prune models that are not AlexNet and VGG? Is that your question?
Possibly.
Yeah, so for example, in the NetAdapt work that we did, we actually pruned MobileNet. We pruned the very small MobileNet, and we're able to achieve higher performance on that. Even on a small, even if the baseline is a very small MobileNet, it's already an efficient architecture, we can still prune that. Does that answer your question?
Do you have any results?
Yeah, so the results are right, they're in the NetAdapt paper. Let me just pull. So these results are all on MobileNet. Right,
okay.
so this is the original MobileNet, and then these are all prune results on MobileNet.
Okay, thank you.
Sure.
Thank you very much for the presentation. We talked about a lot of the constraints from the algorithm as well as the architect, but sometimes there's more constraints from the manufacturer's point of view. For instance, some design may sound very good in theory, but maybe it's very difficult to be produced in reality. So do you have any comments or insights how to keep that into the consider and keep the manufacturer in the loop as well?
Just to clarify, when you say manufacturing, you mean like this is for process and device technology?
Yeah, for instance, how to make these chips, how to deliver this to the market, the whole process and so on.
Yeah, so I would say that that's probably covered by device folks. I mean, IEDM is probably a good conference to go and check that out. So I'm sure, I mean, there's great people working on ways to like reduce process variation on their devices and so on. I think obviously it becomes more challenging as you shrink the device technology down. And then the challenge is for all these processing and memory approaches, you're much more sensitive to them just because typically they use analog-based processing. So we actually have a paper at Eyexam that I'm presenting there tomorrow on that particular topic. How do you redesign neural nets so that they're more appropriate for these type of processing memory technologies that are more sensitive to device variation?
Okay, thank you very much.
Sure.
Thank you for the comprehensive presentation. My question is simple. It's about the filtering now. The core is a 3x3 in the DNN, very common now. But for the design in the industry, and they call the tensor core, some of them still using 16x16 to the matrix computation. So what do you think? What could you advise for those industry practice? Is it better to have a bigger one or a small one?
Yeah, so this is always a very tricky question, right? So whenever people want to build specialized hardware, it's going to be more efficient for that particular block. And if they want to add some more flexibility to it, it's going to be less efficient. So this is, I mean, from an industry perspective, this is also a design choice that they have to make. You need to place a bet in terms of where do you think this field is going to go? You try and build specialized hardware for that aspect, but if you add too much flexibility, it might hinder the efficiency of those particular blocks. So, you know, without I can't predict the future, but like I think those are the things that you need to factor in. So even if you know the matrix size gets larger, the question is how widely is that going to be used? Is it worthwhile to put down hardware just to support that, or is it better to have more, for example, 4x4 tensor cores for other applications? Because typically you're limited by the, like from a cost point of view, you only have so many transistors, so where are you going to allocate your transistors? Right, so it's a business decision.
Okay, thank you.
Sure.
You did a wonderful job describing how designing a model specific for hardware is able to improve performance through the co-design process. My question is once you have designed a model for specific hardware, you could become trapped to that hardware. What is the cost of moving from one architecture to another architecture once you've co-designed for one specific hardware?
Right, so that's a great question. So I think that's why we kind of emphasized for the co-design approaches, it's really important to think through, is this approach a general approach across various different hardwares, or is it just tied towards one specific hardware? Now, sometimes when you tie it to a specific piece of hardware, you might get better energy accuracy trade-offs. I mean, it's just the same idea as well. Like, if you tie it to that, you can do better, but then you lose the flexibility of switching to a different hardware. Versus an approach that might be more general, but it might not be as effective of getting that trade-off. But that's a decision that you have to make in terms of how much do you tie. So, like, I think one process that you could start by doing very general-based approaches, and then if you really, really need to push the efficiency, then you start really tightening the co-design approach with the hardware and the algorithm itself. So it really depends on how much you need to push the efficiency. That's what I would say.
Thank you.
First, great talk. Very, very good. I'm unaware of any toolkits that take advantage of sparse pruned networks. So in some of your works, what did you use to demonstrate speedups in the pruned networks?
For sparse pruned networks?
Yes.
So yes, I think certainly that's still an open challenge to build. Like, I mean, an open active area of research is building hardware for sparse neural nets, actually. So if you look in like all the computer architecture conferences, people are looking at how to build that. So for our evaluations, primarily if we're doing irregular, it depends if it's structured or unstructured sparsity. If it's unstructured sparsity, meaning I can remove weights from anywhere, I think what we use to evaluate that is things like Iris V2, which supports that kind of sparsity. But if it's structured sparsity, so for example, you can think of, in some ways, NAS is also structured sparsity, like removing channels, for example. So NetAdapt removes channels. Then you could actually profile that on embedded platforms because they handle structured sparsity, like existing CPUs and GPU platforms handle structured sparsity much better than irregular or unstructured sparsity. Right.
Thank you.
Thanks.
Hello? Hello?
Yeah.
Yes, you mentioned that in Iris version 2, you use compression from both sides, activations and weights. However, by adding compression, you also sacrifice a little bit of inherent parallelism that that, for example, inference has. I was wondering, how do you tackle that problem, like inducing high compression automatically serializes more the algorithm versus no compression, so how do you handle that?
So in general, I mean, you can process, when you compress, it depends on how large of a chunk you actually compress, right? So you can actually process different chunks that are compressed but not compressed together and process those in parallel. We can talk more in detail offline, but in general, you just have to balance the compression with parallelism, right? So if you fully compressed everything in one huge run length encoding, then it would be very difficult to process in parallel. But usually people tile it up and then compress the tiles.
Thank you.
Sure.
Hello, for these mixed signal calculations with analog noise, is there some way in the training you try to account for additional noise from the analog additions?
Yeah, that's a great question. So there's a huge amount of people looking into that. I think there's two approaches. One approach is to try and train or basically fine-tune the net for a given platform, given its variations, but that can be very expensive. There's another approach, people just generally speaking, can we just factor in noise during the training to reduce the impact? And there's a lot of people looking into that. Thanks. All right, thank you.